Swayam Prabha. Digital India. Educated India.
IIT students, if you want certificate, you need to register. I can tell you the process. Next topic is very important, introduction to OpenMP. This will be given by Sandeep Agrawal from CDAC Pune. Sandeep is a senior technical officer there, and he works on organizing code and users will optimize their code on a lot of different applications and platforms.
So, hi everyone. So we will see about one of a widely used parallel programming model, which is OpenMP, and some of you are already aware of OpenMP, and many of you are not aware. So we have hands-on on it also. So it's most of the thing which we are seeing in the talk. So we'll cover in hands-on also. So please do interact whenever you feel like you have any doubts and all. So this is a good example of parallelism. So it's about Formula One race in which the race car, they have to be after a few laps, they require changing of tires, they require some wing reassembly or some repairs and all. So it has to be, and that time is also counted in their lap time. So they have to be, it has to be done very quick so that the car can have better total race time. And so it has to be done in parallel. So the crew members are ready beforehand, and as soon as they will signal the car to reach a point, and they'll do it in parallel. And so some of the task has to be cooperative, users, they have to exchange tools among themselves, or the crew members, they have to exchange tools among themselves and so on. So it's a cooperative parallelism, you can say. Okay, so the contents that we'll cover is some general concept. Then we'll see what is OpenMP, OpenMP programming and execution model, some OpenMP constructs, so which we are going to use in our parallel programs in our hands-on sessions. And so throughout we'll be discussing some techniques, some concepts. So we'll see how they are applicable for our hands-on sessions. Then I'll also talk about data locality, granularity of parallelization, and domain decomposition. And then we'll conclude with advantages and disadvantages of OpenMP. Then lastly, I have some references. Okay. So here we have a single core processor, though it's no more available. It was generations back such model was available. Now all we have is multi-cores. So in single core, as you can see, this CPU would talk to memory, so it will get data from memory. And in similar way, in multi-core also, so many cores, they are attached to a memory pool, and they'll get data from the shared memory. Now, when we run a sequential program, so let's say my sequential code is running on one core. So it won't be able to make use of multiple cores, even though they are idle. So if I have a long running job, So some of you had questioned also, like if you have serial job, how will benefit from HPC machines or parallel machines. So by default, we do not benefit from that. In fact, it may be the other way around. Performance may slightly degrade also on that system. It can be because of, like, on multi-core environment, you have lesser frequency cores because to maintain the power envelope of the CPU chip. And so earlier, like, we used to see the frequency scaling and they could get on to like 4 gigahertz or so on. Now we are seeing that frequency they are mostly 2.5 gigahertz or so. That's because we are going for more parallelism. So a single threaded job would not benefit much from that. Okay, so we'll just have overview of process and thread. We have covered in the morning session also, first session, process and thread. So it is important because in this talk, we'll be dealing with multi-threading or multi-threaded programming model. And then later on in following days, we'll be dealing with process level parallelism. So how, like, multiple processes, they can be executed in parallel. So process is an executing instance of a program, and it has independent memory space. So whenever a program spawns, it has its own memory space, which is logically isolated from interference by other processes. So they don't have direct access to other processes' memories, even though the memory is physically shared. Thread is a subset of a process. It's also called lightweight process, and it allows faster context switching. So why is it lightweight? It's because it shares most of the resources of a process to which it belongs to, and it has some private space like its own stack and so on. But most of the things it shares from process. So what happens when you have to say I have two threads and they want to time share a given core. So when one thread will be preempted from a core, its context would be not big in size. So it can be faster saved, and another thread can be scheduled on that. So, when we see at the process level, the context is quite big. So when we have multiple threads, most of their context is common, and so they are quite lightweight, and the switching is fast. Threads share memory within processes memory. Threads may have some private data like stacked variables and so on. And they have independent execution stream also, because of which concurrency is possible with threads. So multiple threads within a process, they can be spawned across multiple cores. So we can make use of multi-cores with multi-processes, multi-threads. And if my process is compute bound, so generally I would prefer one thread per core. So it's because if we have more threads per core, so they'll keep on context switching, and which will not be an efficient way. If they are not very CPU bound, they are IO bound, they are dependent upon memory to fetch data, or they are dependent upon storage, getting data from files and all. So we can have more number of threads to occupy this latencies with respect to IO. So a generic shared memory model, it has some characteristics you can have multiple threads which can operate independently but share the memory resources. Then data is not explicitly allocated. That means if I have an integer, let's say integer A within my program, so this A would be shareable across all the threads. We don't need to give private copies of A to every thread. So, so that means we don't have to say that this data belongs to a given thread or so. Then any thread can make any changes, any change to that data, and so that would be visible to all other threads. So this is the way how they can share data among themselves, or we can say they communicate among themselves. Synchronization is explicit, so we'll talk more upon this. So when we have expressed parallelism in our code, so we require sharing of data, or a shared, and so there can be a scenario where we don't get consistent result because across different runs, different threads may be modifying data in a different way. So synchronization is an important part for wherever we have such data dependencies. So now we'll talk about OpenMP, which is an acronym for Open Multiprocessing. So OpenMP is a specification for writing shared memory parallelism. So it provides guidelines, it provides specifications through which any implementation, there are various compiler implementations for it, they have to follow these guidelines to provide OpenMP implementation in their compilers. Then it provides multi-threaded parallelism. Then OpenMP is primarily data-driven, directive-driven. So that means in most of the times we deal with directives in OpenMP. So directives are requests to compilers. They are which if the compiler doesn't support, can be ignored. Your program will still be able to compile and run. So it's kind of annotation to your source code, wherein you say that such parallelism exists in the code, and through that the compiler will, behind the scenes, it will perform certain changes in our code and to make it parallel as per our directives. Then there are runtime library routines. So there are functions which are defined by OpenMP, wherein we can make use of these functions and again express parallelism or control the behavior of our program. Then we have environment variables. So environment variables is once we have compiled our program, so we need not recompile it. But let's say I'm running my OpenMP program with 4 threads. I want to run the same program with 8 threads. So I need not recompile it. I'll just use some environment variable to set the number of threads, and I'll be able to use those threads. Okay, so this we have, and it's easy to create multi-threaded programs in C, C++, and Fortran. So OpenMP provides specifications for these languages. So basically it's an extension to these languages. So why should we choose OpenMP? It's portable. So that means there are some standardization done for the OpenMP specifications, which any implementer has to follow, because of which it is portable. We have several architectures, let's say RISC-based architectures, CISC-based architectures, and so on. And even across a given architecture, we have different flavors within them. So, and then from the compiler's perspective, how they are implementing. But once we have written a source code, we want to be assured that it should behave in the intended manner on any given architecture with any given compiler or environment. So OpenMP provides those specifications, so it's portable. Then it's simple and quick. So that means it's quite easy to do parallelization with OpenMP. We'll see how easy it is. We just have to use certain lines of code, certain directives, and our code would run parallel. Then it provides incremental parallelization. That means like we can parallelize a certain part of the code. We can see the correctness of the program. Maybe we can get performance improvement also, and then we can go ahead with parallelizing other portions of the code. It supports both fine and coarse-grained parallelism. So fine-grained parallelism is like loop level parallelism. We know that most of our computations, they happen in our iterative loops, and so they are like the major source of parallelism, and so they come under fine-grained parallelism. That is, we parallelize loops and we get parallelism. Then there is a coarse-grained parallelism. I will discuss in the later part of the talk. Then OpenMP provides a compact API, and it does not provide automatic parallelization. So so user has to explicitly write within the code to have the code parallel with OpenMP. Now this is like what organizations, they are part of OpenMP ARB. So there is a like architecture review board for OpenMP, which is like across academic organizations, government organizations, and industry. So there are several organizations involved in it who like collaboratively they define the standard for OpenMP. And then many of the OEMs, like original equipment manufacturers, they provide their own implementation of OpenMP. So that's because they know their hardware best, and they can fine tune the OpenMP to perform like best on their hardware. Then we have some popular implementations from GNU, then Intel. So mostly we'll be using Intel in our session because we have Intel hardware. We also have GNU on the system, and we also have PGI compilers on the system. You may use it anytime. Then there are other implementations also. So here we have the history of this OpenMP releases. So it was started about 2 decades ago, and currently we have OpenMP 5.0 release, and like the compilers would catch up with these releases, like whatever specifications are provided in these releases. So they would like catch up with this releases at their own pace. So here you can see like the latest GNU compiler. It has partial support for OpenMP 5.0 and so on. Okay. So OpenMP execution model. So as we can see in this picture, that there is a single thread which we call as master thread. So you can consider it as a process. So this is basically a process which can also be called the master thread. And now when we have some part of the code which can be made parallel, which we feel is like compute intensive, and it can be made parallel. So we'll use OpenMP constructs to parallelize that part, and then we'll have a team of threads which will work in parallel. So having just team of threads doesn't parallelize our work. We have to actually allocate work to the threads. So then only, like otherwise they'll be redundantly doing the same computation as in the serial code. So after that, we can have synchronization. So there is default synchronization, and we can do away also with that if our parallelism permits it. Then again we'll have the master thread, and again we can have a new parallel region with same or different number of threads. So this kind of model is called fork and join model. And the master thread, so that is always part of the team, and it's always there. So some basic syntax for OpenMP. So this is how, like in C or C++, we'll write our OpenMP annotations. So it starts with sentinel hash pragma OMP, and so this is called directive. It's directive to the compiler. If the compiler say doesn't support it, or if he doesn't compile it with the required compiler switch, so like this will be ignored, and our program will run as it would run in serial fashion. So then we can give several specifications here, like several clauses here, through which we control the behavior of our parallelism. So this is the actual syntax, like for creating or for specifying that I want parallel threads. So when we say hash pragma OMP parallel, a team of threads would be created. So the team of threads, so that will be available from the start of this phase till the end of this phase. At this end, it will automatically, the threads will terminate. So when we have a team of threads, so they have a unique identifier associated with them, which is called rank. So this is required to have task parallelism, or to have allocation of work based on the rank of the threads. So we want to identify them uniquely, and there is a unique integer starting from 0 associated with every thread, and it's contiguous till the number of threads minus 1. So here we have the parallel directive for Fortran and C. So Fortran, so this is just like 1 or 2 slides I'll have on Fortran. Then we'll mostly be talking about OpenMP thing. But the same things, the same constructs would be applicable in Fortran also, maybe in just slightly different syntax. So we can have multiple parallel regions, like this is one parallel region, then we can have another parallel region, and so on. So how do threads interact among themselves? So when we say we have a parallel region, let's say I have a problem, I want to compute sum of n integers. So let's say I divide this n, this summation problem into smaller parts, and I give some subset of elements to every thread, and they do their partial summation. And finally, I have to aggregate the result. I have to sum all their results, right? So there we need to have data from every thread. So we'll require some kind of communication or interaction among threads. So threads, they read and write shared variable. This is how they would communicate to each other. So a given variable which is would be shared by default across all threads, and through proper mechanism we will make use of this variable among different threads, and one thread which has affected some modification to a variable, that would be visible to other variable, and this is the way they like interact with each other, share their partial values. But if we have a race condition, that means like if multiple threads, they are competing to update value of a shared variable, so it can lead to inconsistency. It depends upon the relative speed of threads. Like let's say I have two threads, and one thread wants to like make value of A as 100, another thread wants to make value of A as 200. So depending upon which thread executes last, so that value would persist. So in our serial program, this was not intended, right? We would have wanted a deterministic result from a serial program. But here it would depend upon like whether thread 0 or thread 1 is executing faster, who executes it last. So this leads to race conditions. We need to have some synchronization mechanism through which we can like have a consistent result. We can have the desired or the semantics of the serial program maintained in our parallel program. So with synchronization, we can like handle this dependency, but they are expensive. We'll see in our parallel programming that the more we use synchronization, the more we have performance penalties. So, we should have some better way of managing this dependencies. So, one of the way is changing data storage attributes, like instead of having shared model or shared data, we can have private data. And that also improves our cache use. Because if we have a shared data and that is modified by different threads, so what happens that each thread possibly would be allocated to different cores. Each core will have their private caches, and they would have a copy of the shared variable in their cache memory. And if one thread modifies it, so because of cache protocols, so the copies for other threads will be invalidated. So again, they will have to fetch it from main memory. So there is a concept called cache coherency, which is there, which would whenever there is a modified, which would keep track of the copies of shared variables available across caches of different cores. And if any modification happens at one place, so it will invalidate, so that if the other core they try to fetch it, they'll have to again get it from main memory. But one of the problem with that is that cache coherency, that is not maintained at atomic level. So that means if we have faster executing threads, so we may end up with race conditions. So there can be scenario where two threads, they are able to modify it at the almost nearby cycles, CPU cycles, because that is not maintained at atomic level cache coherency. So if we have if we change the storage attribute to private, and so that means we don't have dependency on other threads for that data. So that data would can easily persist in the cache memory. So we will have better cache utilization. So OpenMP is broadly it provides these extensions for parallelism, for expressing parallelism within our program. So it provides parallel control structures, which we have seen, like with hash OMP parallel. Then it provides work sharing constructs. So how we can divide our work. So it can be data parallelism, it can be task parallelism. Then we have data handling, where we manage the shared or private scope of the data. Synchronization we have talked about, like we have to wherever there can be race conditions, so we have to synchronize our data. So we have constructs for that to handle the synchronization part. Then there are library functions and environment variable, to which again we have control of the OpenMP pattern. So these are some of the constructs, though the list would be quite comprehensive, but we'll be touching upon only the few major constructs, and most of the parallelism or most of the performance from the code can be extracted using using these basic constructs in our program. Parallel region we have seen. Then there is a work sharing construct, which like if we have a loop, so we can distribute iterations of that loop among threads. So if we just put OMP for, so my loop would be distributed across the available parallel threads. Then sections, it provides task level parallelism. So let's say I have different tasks, different functions within my program, and so I want these different functions to be run by different threads, so I can make use of sections. Then this is the data scope. We can have shared data or private data, and some of the synchronization like barrier and we'll discuss. So here we have a for work sharing construct. So if we have a for loop and we know it takes time, so we can add OpenMP directive to that, and my for loop will be parallelized. So we have to just say hash pragma OMP parallel for. And the for loop should immediately follow this directive. Then only it will compile, otherwise it will throw compiling error. Then when we say parallel for, so our loops or iterations, they are divided across threads, but how are they allocated to different threads? That depends upon, like, so that also has several policies, and which we can control. So we call it scheduling of loops. So basically it consists of we have four scheduling types, like static, wherein we know prior that what iterations would go to what threads. Let's say I have n threads, so I would know that I have so many iterations, and so these many iterations would be divided by n, and let's say I have the ceiling value of it, and so the first set of chunk would be given to rank 0, next set of chunk to rank 1, thread rank 1, and so on. So that is static scheduling, and which is deterministic in nature. So that means even when we run it multiple times, we'll see with the same number of threads and iterations, we'll see that the same ranks are picking the same iteration within the loop. Then, so static is good where you have a load balanced computation, wherein your different loop iterations, they are taking almost similar amount of time. So it's good for that. But if let's say you are dealing with sparse matrices or irregular computations, so this strategy will not be good, because certain threads would be idle and certain would be oversubscribed. So there you can go for dynamic thing, which at the runtime is decided like based on the speeds of the threads, how they are able to finish their work. They'll pick subsequent iteration. Then there is a variant of dynamic scheduling, which is called guided. So in guided, again, like we have threads picking iterations as they complete their assigned iterations, but there is a certain formula like through which what iterations or what number of iterations they would pick up. We'll see that. Then we can defer the selection of this policy to runtime also. So from our environment variable, we can control like which policy we want. So instead of hard coding it, we can control it through environment. We can also check like what is giving us the best result. Then later on we can hard code it. So static schedule. So this is a work sharing construct for loops. So when we say parallel for, so after that we'll give schedule. If you don't give it, so compiler will by default take this as static. It will do it, but the way the compiler would do it is generally like all my iterations, they will be divided across the number of threads, and whatever chunk comes per thread, so it will be allocated at one go to all the threads. So we may not want it that way due to performance reasons, like we have a lot of shared data, and so if we are dealing with big amount of data at the one go, so that may not be good for our cache utilization perspective, right? So for better cache utilization, we always want to stick to a smaller data set. So we would like to assign our computations or adjust our computations such that it tries to exhaust a smaller data set with respect to computations, then it would use the other data sets. So here we can, so by default, as I mentioned, like a contiguous block of data would be given to a thread and then to a next thread till the last block goes to the last thread. But we can have control over that through by setting this to some value. So that many iterations would be allocated per assignment. So whenever new assignment happens, assignment of loop iterations to a given thread, so it will happen in value of this chunk. So it will happen in this chunk. So this is a block cyclic kind of distribution. So generally it comes to this ceiling number of iterations divided by number of threads. And if we have when n is not specified, if we have n specified, then first n iterations would go to rank 0, next n iterations to rank 1, and so on. It would happen again in a round robin fashion. That means in block cycling. It is deterministic in nature, and here we have an example, like if we have 16 iterations and we have 3 threads and we have a specified chunk size as 2. So first 2 iterations would go to rank 1 or rather rank 0, because the ranks start from 0. So let's say this is thread 0 rank, rank 1, rank 2, So first two iterations would go to this, then 3, 4 to next rank, 5, 6 to next rank, and so on in a cyclic fashion, and the remainder would go to the last thread. This is dynamic. So similarly, we have chunk size in dynamic also. So this chunk size, if we don't mention, so it's 1 by default, but that 1 has will have overheads with respect to it. We can say that 1 is better because it gives a finer control on the like relative speeds of thread, but it has overheads also because the runtime system has to dynamically like assess which thread is now available and which iterations to assign which thread. So that will have overhead. So it's generally better to have some reasonable value for n. So when dynamic happens, if you run it multiple times, you will see like different ranks, and you can like here print thread rank and the loop value of loop index, through which you will come to know like which rank is picking which iteration number. So you will see that different runs will may have different values. Then guided. So guided is like dynamic assignment only, but the chunk sizes, they keep on decreasing. So with every assignment, the chunk size keeps on decreasing, and then we can put a threshold to that. We can put a number here below which it won't assign the number of iterations. So the chunk size, generally it is maximum number of iterations, remaining.
Excuse me. In the dynamic one, the length of that block, what does that indicate?
Length of the block. This chunk size?
Yeah, in the diagram, the figure.
Okay.
What does that indicate?
Okay. So you can see that they have different compute time for different iterations. So this is having larger work than with respect to 2. So it will pick only one iteration, and so since we have not assigned any number here, so the granularity will be one iteration per. So that is in case of dynamic.
In case of dynamic, you mentioned that the thread pick up the.
So that is the runtime, OpenMP runtime implementation. So which will keep track of like what iterations are remaining and what threads they are still in like execution phase, or they have like completed their iterations. So it will is.
The OS is not doing this.
No, OS is not.
And the master thread has no role in this. This is totally the runtime.
Yes, yes. And the master thread isn't any like special thread. It's just that it exists throughout the life cycle of execution. It isn't any special thread per se.
How the ranks are initialized for the
How are ranks?
are initialized for the thread?
Ranks are initialized.
T1, T2, T3 is there.
So ranks they'll be initialized let's say in a contiguous manner. So whenever like you say parallel for or just parallel, so there a team of threads is created. So as soon as the threads is created, so they'll be having rank associated with them.
You mentioned like for different ranks will be having different values for different threads. Like do they use any kind of pseudo random generator for this, assigning the rank?
No. So that's because like always on your system you have some processes running on the system. Of course, to manage the system there are daemons running in the background and so on. So it's all, and they are also switching across different cores, these processes. So it's not that core is 100% available, or the cache related to that is fully free, and so on. So those all have dependence on the execution time taken by a thread for that iteration. So because when it is executing, it has to get its data, so depends upon that and the amount of computations and so on. Then
So now in the same for loop, different iterations run simultaneously on different cores. Is that right?
Yes.
So if there is a data dependency between two iterations, how is that managed?
That we'll see. Then we have schedule runtime. So that means we can defer it, this scheduling to runtime, and through environment we can pick one of the three, and we can see like how our code is performing with respect to that. So here we have data scoping. So data scoping plays a very important role in the performance of our code. So they can help us in minimizing the synchronization of our program. So it depends upon how we can make good use of this data scoping. So we have a shared data scope. So that is by default there is a shared. So all variables, all our data is shared across all the threads. That means any thread can modify any part of data. Then we can have private data. That means a thread would own its local copy of the data, so which is not visible to any other thread. Only that thread has that copy. So every thread has a stack, its own stack associated with it, where our automatic variables they are generated. So whenever we say define the scope of some variable as private, so they will be assigned to threads private space. Then we can have a special private type, first private. So this means we want to inherit the value of some prior part in the program to our private variable. Otherwise, generally these private variables they'll be initialized to some value, or it can be junk also. It depends upon implementations. If you use different compilers, you will see some are initializing them, some are not initializing them. And then last private, so we'll see in the later slide, and default also we'll see. So in shared, we have data shared among the team of threads. Each thread can modify any data, and so because of this shared nature, the corruption is possible. That means there can be race condition, two or more threads they want to simultaneously update a shared variable. So that can result in unintended output. So it is user's responsibility to maintain the correctness. So this provides shared clause, it provides us the simplicity of programming, but it also poses risk to the unintended sharing of data. Then private clause, this is how we can define data or variable as private. So here we have a variable named PID, and we are making it private. So when we say private, so as soon as this is encountered, so local copies for every thread will be created in the memory space of the process. So every thread will have its own copy of TID. So let's say I want to get the rank of a thread. So so this function just gets the rank of the given thread, and so rank is definitely unique for every thread, so it cannot be a common value, so it has to be private. So we have defined it as private, and we can make use of this ranked value for distributing or decomposing our work also, if need be. Okay. So first private is like a private. Again, every thread will have its own copy, but like private, or in the this case, PID, it was not having any predefined value, or it can just have 0 or something if the compiler initializes it to something, but it will not have user defined defined value. But here, if we want to inherit the value of in B from the previous part of the program, so we can say it as first private. So it will value would be initialized to this, right? Then we have last private. So as the name indicates, so whatever is the last value which should have persisted in our serial program, so that value is intended from the last private scope. So that means whatever the last iteration of the loop be, follow this parallel region. So when the this parallel region it finishes, so the value from the last iteration would follow. So it doesn't depend upon the speed of threads. So threads, so the last iteration may be executed earlier than other iterations. Let's say I have iterations distributed across threads. So last iterations are finished first. The thread which is holding intermediate or beginning iterations, it is still executing. It may happen so, but the value which is going to be here would be from the last iteration. A is a global variable. No, A is a last private. Last private. So B is first private. It is getting its value from here. B is equal to 51, so it will be 51 here. Then I is private, and by default, the loop index variable is private, even if we don't specify it. So the loop index has to be private, right? Then only different threads will be able to work on different iteration values, iteration numbers, right? So it has to be private. So, and it is by default, but we can also write it.
If you just mention hash pragma OMP panel for code a simple for loop, how many, what's the chunk size? What's the default chunk size?
If we mention only parallel for,
Yeah.
so what will be?
What will be the default chunk size?
Default chunk size?
Yeah.
Okay, so default it will go static scheduling,
Okay.
and the chunk size would be iterations divided by number of threads. So ceiling value of that.
Sir, I is private because we want it to be controlled only by master thread. Is it?
No, it has nothing to do with master thread. So I is private because we are seeing for here. So for is a work sharing constraint. So it is a form of parallelism in OpenMP. So for means you have some sets of iterations, and so that is work which can be decomposed into smaller sets of iterations. And so whenever we say with OpenMP, we say for, so that means we are intending to distribute our loop iterations among threads. So when we do that, so automatically the index variable for this loop will get privatized. So every thread can have its own value, and they can independently work on iterations.
I did understand last private, but can you elaborate?
First private, okay. So first private is like, let's say I have two parallel regions. two different parallel regions. One parallel region is generating some output, some partial output, and that output, that value we would like to get in the next parallel region. And so in the end, again, like we'll be using that value, but we also want to have it private, because say we have some data dependency conditions and we want to avoid that. We want to have private scope. That will be clear, data dependency will be clear in later part. So in that case, we want to use the value of which was there before the second parallel region, right? So first private would enable us to have that value. If it's only private, so that value will not exist here. So we can set default data scope also. So whatever we choose, like if we choose private, so by default all variables which are present inside the parallel region, they will be treated as private. We can have them as shared, we can have them none. That means there is no default scope. We have to explicitly define each and every scope for each and every variable. So this is like the most safe way. So wherein we have to explicitly define for every variable like what scope it should have. If we don't give anything, so it's what is it? If we don't give any like a storage attribute, share. It's share. So there are some more clauses, parallel directives. So these are like we'll see each of them: no wait, if, and reduction. So no wait. So whenever we have a parallel region, we have a synchronization at the end of that parallel region. So this is because like let's say after the parallel region, we assume that data from the parallel region would be used after the parallel region is over. So if let's say we don't have that wait at the end of the parallel region, so what will happen if master thread, if it comes out of it parallel region, so it may have some value which is an intermediate value. That value was still being worked in the by other threads in the parallel region, but master thread has come out of it and it's going in the later part of the code. So there can be inconsistency in our output. So to ensure that this doesn't happen mistakenly, so default there is a wait at the end of every parallel region. So at the end of parallel region, all the threads will be waiting there for others to finish, for each of them to finish, and then only they'll they'll terminate and the master would proceed. So if we say no wait, if we know that there is no such dependency in our code wherein we should wait, so we can say no wait. And so it can happen in a very, like if you have embarrassingly parallel kind of task or work, so wherein like computations done by any thread is not dependent upon any other threads. So there we don't need this synchronization, this barrier, implicit barrier, we don't require it. And for better performance, we can say no wait. So it will enable like threads to proceed in if there is later part in the parallel region, or like they can terminate. If clause, so if clause is there So it takes a call whether a particular region has to be made parallel or not. So
is it possible to have a barrier before another parallel section?
before,
Before we have another parallel section?
yes,
Explicitly before the parallel section starts, can we have a barrier? What is
so
the
barrier you can have anywhere unless and until every thread is able to call that barrier to reach that barrier. It should not be within if condition and all. And secondly, it has to be within the parallel region. So unless the threads exist, we cannot have barrier.
Okay. So the barrier, so either for, if we have like two parallel sections that are not dependent on each other, and we have a third section that is dependent on the first two, so we have to have the barrier at the end of the second section.
Yes, we can have. But then these three sections should be enclosed within a larger parallel section.
For the close first private, is it broadcasting the B to the all the thread?
Is it broadcasting?
B to the all the thread.
You can say so.
So it's in the cache that resides in the all thread.
So you mean to say it resides on all the cache? Cache.
Private cache, L1 cache.
So that depends upon like so when you say private or first private, so what happens that local copies is generated, but that will be generated in your memory. So process has the parent process has that all its executable code as well as all the data with respect to some memory address space, right? So it will be initialized there. It won't be there in cache memory. Once the thread would call this, use this variable, then only it will come to from main memory to it will come via cache. So we can have several parallel regions. If some of the parallel region like can have different workload, like a smaller workload, which is dependent upon like some conditions. So we can have if condition to that, because we cannot say that the more we parallelize, the better we'll get, because it depends upon the amount of parallelism also, amount of work also. If a small amount of work is divided on large number of threads, so that will have more overheads than the benefits that would reap from parallelizing. So it can even lead to more time than the serial code. So we should be cautious that if certain work is there, whether we should parallelize it or not, or if we should parallelize it with what many number of threads. We can have smaller workloads parallelized with the smaller threads and larger with larger number of threads in a given program. Reduction clause is quite useful, and you would see that in commonly used operations like mathematical operations, logical operations, which you want to do across some data elements or some vectors. So this can be very handy, reduction clause. So when we do certain standard computations, we would like to, when doing it in parallel, when data dependency is there, we have to write our own logic and synchronization or scope of data to have that thing in parallel. But with using reduction, we can have it simplified. So for example, I want to add from 1 to n, and so this is what I am doing it here, and the result variable is shared across threads by default. It will be shared, right? But now when I want to do this, So since it is shared, so either we will synchronize this so that different threads don't modify it at the same time, or we change its attribute, data attribute, we make it private or so, something. So rather than doing this, since it's this operation can be reduced this operation can be combined into a collective operation, so we can use reduction in this. So wherein we say what operation has to be done and what is the operand. So internally, OpenMP will take care like how to get this thing done. So what it will do is it will create local copies or threads for this variable, and then finally each thread will have their partial results, and data will be added from all these partial results or reduced from these partial results. So this is called reduction operation. Then a user can have his own operation defined also. So you can have it defined. Another work sharing construct is section directive. So section is like kind of, it provides task parallelism. So you have different tasks. So here, let's say in case of loop, we were having data parallelism. So different iterations of the loop. So they were like, so each iteration was probably doing same work, but on a different sets of data. So, if we don't have such kind of work within program, if we have, say, we are having functions, function 1, function 2, function 3, or not even function, but we are having certain parts of code which can be run independently. So we can consider them as tasks, and to sections we can assign these different tasks to different threads. So here we will say OMP sections. So now threads will enter this, and whichever thread reaches this first OMP section directive, so it will execute that part or that block of code which is within this section. And other threads, they'll bypass it. So only one thread will execute one section. Other threads will go past it, and they will, whichever thread comes first to this will execute this, and so on. Single directive. So there can be a scenario where we, let's say we want to do some input output, read from file, write to a file, or any other thing other than input output also, which has to be done by only single thread. So we can define it as OMP single. So any thread can pick this value, but only one thread will pick it, others will go past it. But the single directive also has implied barrier at the end. So here other threads would be waiting. So while one thread only would execute this block of code, but other threads would be waiting here. So there is an implied barrier at the end. Then OMP master, and so only master thread would execute this part of the code. So this is an example of a race condition. So let's say we want to find largest of a list of elements, and let's say I have we have initialized this max to 10, and max will hold the value of our largest element. So let's say we have n elements, and there is an array A of n elements, And now we'll compare each element with this max value. So max value we can also initialize to A0, and so this condition would allow us to update the max variable if this is true. So when we do it in parallel, so different threads, so we can consider this example, thread 0 and thread 1, and they read the current value of from the list of elements as 12 and max value is 10, and this thread also reads another element and its value is 11. So both are satisfying this condition and both would try to update the value of max, right? So whichever thread will execute last, that value will be retained, right? So this is a race condition. So if let's say thread 1 executes last, so value 11 will exist in the thing, though value 12 should have been the right answer. So this is a race condition. We have to avoid this race condition. So how we can do this? We can use critical section for this. Critical section is a synchronization construct, and so what it provides is exclusive access to a thread at a time. So whatever region we have specified under critical section, so only one thread will execute it at a time. So no two threads will compete for it at the same time, or they can compete, but only one thread will be assigned to this. But all the threads will take hold of this critical section and they will come and execute this block of code. So as we can see, since only one thread gets access to it at a time, so this serializes my code, right? So we won't have parallel performance from this. So that is why the synchronization primitives they cause performance penalty. Then there is another synchronization which is barrier. So barrier is like there is a defined point where all threads should reach, and only when all of them reach, they can proceed further. If any thread has not reached this point, all other threads will wait for it. So here we are determining the ranks of thread, and we are saying if PID is equal to 0, we are setting some value of x. And then for all ranks which are not 0, for all other threads, they'll print this one, right? So different threads will print may print different values here, right? So because while thread 0 is executing this, other threads will can execute this, and at that time the value of x was not changed. So they'll have the this value, different value here. But if we have a barrier here, so that means all threads will synchronize here, and only thread 0 was modifying it. So this value would be available across all threads. Then atomic directive is like your critical section only. The only difference is that it will work on single statement. It won't work on multiple statements. So atomic is supported by your hardware, and it works on only single line of code. Barrier part. So the barrier part is like you are modifying certain data, and that too by only a given thread, or maybe a few threads are modifying certain data, but we are going to make use of that data by other threads also. So they can have the previous value of the data. Other threads can have the previous value. We don't want that. So it's kind of synchronization that will put a barrier. So barrier will actually flush all the updated. It will kind of do, you can say, cache synchronization, wherein like all the updated values. Let's say thread 0 is doing it. So thread 0 will have the updated value in its cache, right? But other threads are having older values. So when we say barrier, those values will be flushed out from there, or that will be invalidated from the cache. So now when other thread wants to access cache, wants to access X, so they'll have to refetch that value from memory. There are some library routines, like we can set the number of threads. We pass an integer to it, and this is how we can like control the number of threads within our program. And we can give make use of this multiple times. So for different parallel regions, we can have different numbers here. Then we can get the number of threads. We can retrieve this value inside our program. So this is required because of two reasons. One reason is that when we are setting the number of threads, it's not definite that we'll get those many number of threads. So it depends upon the OS whether it is able to furnish that many number of threads or not. So let's say we are requiring, so up to a reasonable number, generally it will always furnish. But if we are requesting large number of threads, it may happen, or there are multiple users each are requesting thread, it may happen that it may not be able to give that many number of threads. In that case, it will give fewer number of threads, and so we won't have this number, we will have some different number which we want to get in this. And secondly, most of the time we generally don't hard code within the program how many threads we want. We keep it for environment variable. We set it to environment variable depending upon, like, we have a compiled code, and depending upon how many cores we have and so on, we will decide the value that time. So within the program, we don't know like what will be the number of threads. So we can get that value through OMP get num threads. Then we can get the rank of any thread. So this is sometimes useful to get the rank of threads based on which like we do certain operations. Then there are environment variables. So environment variables means like what we are setting in our shell. So we set certain variables there which provide control to our program execution, or to the resources, OpenMP resources that we are asking for. OMP dynamic. So this is like if we set it to false, so that means whatever number of threads that we are requesting, if we are requesting from within the program or through the environment variable. So I am saying that I want those many number of threads. If the OS is not able to provide, so my code will not run. It will give an error that we don't have that many number of threads. But if I set it to true, so we can even if we are requesting, so OS can bypass it and it can provide lesser number of threads. Nested So we can have nested parallelism, like let's say we have two for loops, one within the another. So we can have this nested, we can parallelize both of the for loops like hash pragma OMP parallel for. Again, we can have OMP for the or parallel for the other region. So we have nested parallelism in that case. So what will happen that let's say in the outer region we have 4 threads, and in the inner region we are asking let's say for 5 threads. So what will happen that each of the 4 threads from the outer region will create 5 threads, or will have in total, each thread will have 5 threads. So altogether we will have 20 threads in that. So that is nested parallelism. Okay, so this we have covered. We can control number of threads in 3 ways, and these 3 have certain priority. So this has the highest priority through a clause. When we are creating the parallel region, there itself we mention how many number of threads we want. So we pass that number here. So this has the highest priority. Then this library routine, and then this environment variable. So if we set all the 3, so we will see that this value will be taken. Any questions? So briefly we will touch upon data locality. This is important for performance, and particularly in today's system wherein we see like having large number of multi-cores. So earlier, like there used to be that in our multiprocessor system we were having something called as North Bridge, which would provide access to our memories, RAM, DRAMs, and so these are the DRAM chips. So it would provide access to those. So what will happen, all these multiprocessors, they will have common access time to the RAM, because they are accessing it through that interface, the North Bridge. But now we have memory controllers on the chip itself, on the CPU chip itself. So what happens, these memory controllers, they talk directly, they are directly connected to the lane which is connected to these DIMM modules. So this provides locality of memory to different processors. So this CPU can be multi-core, it can have several cores within it. Again, this CPU can have will have multiple cores and so on. So what will happen, cores inside this CPU will have faster access to this memory area. If they want to access memory area of this, so they'll have to go through this controller. So it will come like this, and it will have slower access to that. And similarly, there is a crossbar switch which is connecting different processors. So that means we have different access time for different parts of the memory. So now when we have a program and we initialize our data and then we parallelize our work. So what happens that we generally don't have data locality in our parallel program. That is because, let's say my master thread begins the program and it initializes an array of elements. So master thread, let's say it is running here. So it will assign, it will occupy the memory address here. So whatever is nearer to it, provided it is available. So this happens at the OS level only, because the OS is aware of NUMA, which is non-uniform memory access, and so it will default, like enable this master thread or the process running here to have the nearer memory assigned to it. Now, when we have OpenMP region, we are creating multiple threads. So those threads will be spawned across all these cores, right, on all the 4 processors. And so what will happen, threads from here will access memory region here, right, because all the data is placed here. Once they have accessed, that data will be available in their cache, but cache memory is very small, right? Whenever like they'll be accessing data which is not present in cache memory, so some data would be evicted from the cache memory, newer data would be fetched. And again later when they want to reuse that data, earlier evicted data, they have to get it from here only, right? So this provides a larger latency for the program. So by initializing data, we should try to initialize it on multiple threads at the same time, so that when the threads are allocating it or initializing the data, so they'll have that data placed nearer to them, right? Let's say I have declared an array inside my program. I have said int A100, 100 elements of integer type I have said. So when I compile such program, so I'll be provisioned with that much memory space in my through my compilation. But that memory space would not be mapped onto the physical memory space. So we'll have a virtual memory space for that. So for all these data that we have declared. But that will not be allocated in physical memory space. That will only be allocated when we are actually working on actually accessing that data. So whenever we are initializing or we are accessing that data, so at the first touch, they will be mapped to my physical memory, and whichever thread is like touching it first, so it will be probably mapped to its nearest memory. So in that sense, we'll have data locality. So this also gives us a performance improvement. And besides, when we do initialization in parallel, so that also gives speed up because multiple threads are able to initialize the data in parallel. So that also gives us a second advantage of speed. And then we have, so generally it happens that when we have multiple threads running, so these threads will like, they will not be holding the CPU for all the time. So what will happen that certain times they'll wait for the data to come. So that time like they may get preempted. Some other process or system threads would run some CPU cycles on there. So what would happen that this thread would not necessarily be allocated the same CPU core. It can be allocated some other CPU core later time. So its context was saved, but that data is like its cache data and all that is not available with that thread anymore, right? So when thread is running on one core, so that core will have some private cache memory for it. So when it was preempted and this thread was allocated some other core, so the data would not be available in that core. Again, so it has to be fetched from main memory, which is very costly, which makes CPU idle. So this would not be a good thing. So we can have CPU pinning. That means we can define certain way in which we say that this thread will be allocated to this CPU core. Okay? So in that sense, the thread will always be mapped to that, will be pinned to that core. So if the thread is waiting for some data, other thread has to run, that's okay. But that thread will, whenever it will be scheduled, it will be again running on that core.
So, so
so if we initialize this data using one pragma OMP for loop, and then we use this data in another loop, so because this which thread will, for example, if we're not using static for loops in this, which thread will actually take that data will not be really fixed, right? So in that case, this scenario can happen that we actually end up using more time and there's more latency due to this.
Exactly, you are very correct. So that would happen. So because of to handle such thing, there is a mechanism we'll discuss. So that is okay. So I'll discuss that. How we can handle it. Okay. I think I have just 3-4 slides. Is it okay? Or? So granularity of parallelization. So let's say we have two parallel regions here, and so as you had mentioned, like you were asking, so we have a team of threads here, and they would be assigned some data here. Though like it's not certain yet here, but I come to your question. So here what we are doing is we are trying to have better data locality with coarser parallelism, and secondly we are trying to minimize the overhead of parallel region creation and termination. So here we are having two parallel regions. The parallel region is created here. It is it terminates here. Again a parallel region is created here with this parallel directive, and again it terminates at the end of this race. So there are overheads of thread management in that. So we can like have a bigger parallel region. So we can do like OMP parallel. So with this parallel directive or construct, a team of threads will be created, and this team of threads will be executing this part of code. So now the team of threads, when they encounter this OMP for, so they'll distribute the iterations of this for loop. Now here we don't have to say parallel again. If we say parallel again, so nested parallelism would be created for that, which we don't want. So here work will be distributed. Again the same threads will come here and the work will be distributed here. Then there is a way of data distribution called domain decomposition. So in domain decomposition, let's say you have a domain, and then you divide or decompose this into several parts for every thread. And why do we do that? Is for data locality. So as you were mentioning, that threads in different parallel regions, thread would migrate, so thread would be executing on different core, and or they can like even if thread is executing on given core, but it may work upon different sets of data, right, across different parallel regions. So here we are defining the sets of region that a given thread will work upon. So we are defining that. So whatever number of say work or iterations that we have, we are dividing it among threads, and then I am creating a start value and end value for the iterations for every thread, and this is the rank of the thread, which starts from 0 to number of n minus 1. So when we when this is computed, so we get contiguous disjoint values for different threads. So let's say we have 100 number of iterations, n is 100 and number of threads is 10. So for thread 0, so the chunk value would be 10. Right? For thread 0, start point would be 0, end point would be this is 0 plus 1, so into chunk, which is 10, So its endpoint would be 9, so 0 to 9. So 10 array indexes it will work upon. And then we have next thread, rank 1. So it will pick from 10 to 19. Next will pick from 20 to 29 and so on. So this way we have data divided across threads. And then these values would work as indices to our array elements which we are accessing. So we have kind of divided our domain across different threads. So here we have some tips for identifying loop level parallelism. We have iterations say from 0 to n. So we don't know whether there is dependency across iterations or not, because if there is dependency, just by simply putting parallel for, that can give us wrong results. So we can run the loop backwards from n to 0 and see if we are producing the same result. So that is one of the way. Then load imbalance can happen due to branching statements. So we can use schedule dynamic for that. Then for less workloads, we can use a smaller number of threads. And then we can have parallelization of initialization of input data. So this will give us speed up because of parallelization, and then it will also give us data locality. Okay. Advantages and disadvantages. So this shared address space, it's user friendly. We can see that just by using a few parallelism constructs, we can parallelize our code, and even very big codes, they can be well parallelized by using these constructs. So it provides ease of programming. Data sharing between threads is fast and it's uniform. So this is with respect to like message passing, which we'll be seeing tomorrow. Then we can have incremental parallelization. We parallelize one by one different portions of the code. Then we don't have to worry about how the threads have to be managed, like in some other threading models like p-threads, wherein like we have to create threads, we have to manage that thread. So a lot of code has to be written for creating and managing the thread itself. Then it is directly supported by compiler. So we'll just have to give certain switch to the compiler, and it is supported at the directly at the compiler level only. Disadvantages are that internal details are hidden. So though it provides a simplistic model, but we don't have very high flexibility with respect to OpenMP. Like other p-threads provide us a finer control of like handling the threads. So they can be efficient, but they can be very complex to manage and code. We have to specify synchronization, so that is an issue. Cannot run across distributed memory, so I cannot run one OpenMP program on two different machines. So it will run only within a machine. A single instance of the program cannot run across two machines. Then performance is limited by memory architecture. So whatever like we have seen NUMA and UMA, so it is limited by the memory architecture, the cache policies and all, how they are making, because most of the data is shared, there can be issues like false sharing and so on. So it depends upon the memory architecture. Then there is a limitation of scalability of such architecture. So it is because when we have shared data path between CPU and memory, so when we have more number of cores and more paths, so what happens that the traffic for accessing shared data increases geometrically. So as we scale the number of processors and memory, so the amount of traffic it increases multiplicatively. So there is lesser scalability. So So just consider that we are using certain synchronization, or at the hardware level, there will be cache coherency mechanisms and other things. So they will be causing lots of overheads here. So because of which the system is not very scalable. Then it requires OpenMP support. Of course, if you don't have a compiler which doesn't have OpenMP support, so you won't be able to use it. Then bigger shared memory machines, they are more costly compared to like you can have a smaller two machines with the same number of cores. So instead of having like 100 cores on one machine, we can have 50 cores of two machines. But of course, my one program will not run on these two. But there will be 100 core machine would be twice, much more costlier than twice the cost of 150 core machine. So this is how we compile it. I will demonstrate it. We have to use with GCC. We have to use this switch -f OpenMP, and with ICC we have to use -q OpenMP. These are some of the